All right, you guys, can you guys hear me? Okay, let's continue then. Continue our discussion of electromagnetic waves. So, oops. I want to talk about some properties of these waves. And then I'll talk about the mathematics, a little bit of the mathematics behind it. Not a lot, but let's talk about some of the properties of these waves. And the figure that you see there shows you the electric field, the magnetic field, and the direction of travel of the wave. So the electric field is perpendicular to the magnetic field, which is perpendicular to the direction of travel. Like the direction of travel of the wave is perpendicular to both of them. And I'm going to talk about the kind of waves that are periodic. The source of the waves is due to some oscillating source. And if you're far away from the source, you have waves that oscillate back and forth in time. Let's say this is the electric field. This is time. The wave repeats itself periodically as it travels through space. The time that it takes for the oscillations to repeat themselves, for the electric field itself to repeat itself, is called a period. One over the period is called a frequency. If you plot the electric field as a function of position, and I'm drawing this as a one-dimensional field, one-dimensional vector known as 3 dimensions, the distance the wave travels before it repeats itself, let's say the distance the wave travels when you have a peak again, or when the amplitude is the same again, is called a wavelength. If we want to find the speed of the wave, is going to be the distance traveled in one period divided by the period. And that's equal to the speed of light. But since 1 over t is equal to the frequency, we can write the speed of light as lambda times f. We also define the angular frequency as omega, which is 2 pi times f. Additionally, we define something called a wave number, with the letter k is 2 pi over lambda. And this is related to the momentum of the wave. Okay? So a lot of times you'll see this term, the wave number for k. It comes up often. Now if we take omega over k, which is 2 pi f times 2 pi, divided by 2 pi over lambda, you get f lambda, which is the speed of the wave. Now we also describe the wave in terms of the amplitude of oscillation, E max. Normally when we describe electromagnetic wave, we really talk about it in terms of the electric field, but we should also realize that the magnetic field is always there too, like you see in that figure. The electric field and the magnetic field are in phase, as you see in the figure. It's just that their orientations are 90 degrees apart. So let me say it again. The oscillations of the electric field and magnetic field are in phase, but they're 90 degrees apart in terms of orientation. Any wave that oscillates in a plane like this is said to be plane polarized. And that's an important thing that you would talk about in 215 when we talk about polarization of light. So those are how we describe the wave. We describe the wave in terms of its maximum electric field or the magnetic field, but usually it's the electric field, its frequency, and its wavelength. Now, where does all this information come from? It comes from solving Maxwell's equations. If you solve Maxwell's equations under various conditions, you get an equation that represents the wave. An equation that describes the physics of the wave. It's called a wave equation. If you take Maxwell's equations and you look at the case when you're in empty space, the sources are far away, you can derive the wave equations under those conditions, and you get the following.
Professor?
Yeah.
What does it say at the top there? It says E is perpendicular to B, and there's a glare.
And then perpendicular to the direction of travel.
Okay, thank you.
So if you manipulate Maxwell's equations for the conditions where you're far away from the source in a vacuum, you get two sets of equations. And yeah, they're partial differential equations that you have to solve. One is for the electric field and one is for the magnetic field. And I actually did this in one dimension. Remember that this is 1 over c squared. And then you have to solve this. And there's techniques to solve this. We're not going to talk about we're not going to solve this. Now in reality, there's two other terms here for the derivatives with respect to the y direction and the z direction. So the left-hand side usually has two more terms here, one for the y and one for the z direction. And solving these is hard. Now for these kind of cases, it's not that bad. If you have a wave that travels along the x direction, you can show that the solution, when you solve these wave equations, when you solve them, you get equations that are of this form. The electric field I'm going to put the vector here. So the electric field is some function of x and plus or minus ct. If you plug these into this equation, you'll see that they actually form a solution. And what I mean by that, if you take this and put it here, take a derivative of this twice, using the chain rule, right? Take the derivative of that twice with respect to x, and then take the derivative of this twice with respect to t. You got to use a chain rule. You got to do it twice. You can show that the left-hand side and the right-hand side are equal. Now, the plus sign means a wave traveling in negative x direction. The minus sign up here means a wave traveling in positive x direction. Does that sound weird to you guys?
Yeah.
So let me illustrate that. Let me illustrate that. So let me choose two coordinate systems. Here's x. Here's x prime. X prime is moving to the right with speed. Let's look at the case where it's moving with speed v, okay? Let's not worry about the fact that it's moving with the speed of light. We can do this in terms of mechanical waves. And how do I write? This is the coordinate x prime. Now x is equal to x prime plus vt. Isn't that true? According to this person, the location of this point is x prime. According to this person, this object is at a distance x prime plus vt. Isn't that true?
Yeah.
And x prime.
The bottom bar is t, right? The bottom line.
Yeah, yeah. And then
okay.
X prime then is x minus vt. Isn't that true?
Yeah.
So imagine a wave like this. Imagine a wave traveling with this reference frame. Okay? Imagine you're on the wave, you're moving with the wave, and some person over here is watching this wave go by. This thing that you see here, this wave is some function of x prime, right? This location is some function of x prime, right?
Yeah.
But if I were to write it in terms of this person's coordinates, isn't it true that this is going to be x minus vt?
Yeah.
Isn't it traveling to the right?
Yeah.
So the minus sign means it's traveling in the positive x direction.
That makes sense, yeah.
Okay. Okay. So that's the general solution, but more specific cases is when you have an oscillating source such that the electric field can be written as E max cosine of kx plus or minus omega t, and B equals B max cosine of kx plus or minus omega t. And I say, wait a minute. You had x plus or minus c times t. Now you have a k and omega. What did you do with that? And then whatever the direction is, I'm just going to put some unit vector that's perpendicular to x, to the x direction. Okay. you might be saying, how come I have a K here, but I have an X and a C here? Let me rewrite this. And these are just generic directions, okay, that are perpendicular to X. I can write E equals E max. Cosine, factor out the K. And what's omega over K? Well, it's C. So now I have it like that. And then this still satisfies the equation. So I still wrote it as X plus or minus C times T. This is the same thing as this. It's still valid. And we usually write it in this way out of convenience. Okay? So this form is equivalent to this form. There's just a K missing there. And that extra K doesn't really do much.
That's just a constant, isn't it?
Yeah. Okay. Now, these represent waves that are far away from the source. And one of the things that's weird is that the amplitude is constant. In reality, it's not. Okay, but when you're really far away from the source, this doesn't change much. In reality, this guy depends on 1 over r. So if you plotted the amplitude as a function of r, it goes like this. But when you're out here, this doesn't change much. And so we write it as a constant number. But like I said, when you're far away from the source, this is asymptotically approaching 0. It ain't going to change much. So the error in making that assumption is not that great. Suppose I give you, I gave you these equations to represent electromagnetic fields in the magnetic field. How would I know that those actually represent electric and magnetic fields? How do I know how do you know I'm not lying to you? Well, this represents the physics governing the wave. What would you do if you're given that E? Well, you plug it into this equation, right? You take the second derivative of E with respect to X, figure out what that is.
And if it equals the other thing that it is, right?
Yeah, that's it. You just got to see that the left-hand side equals the right-hand side. That's all we can do in this class, right? Because we're not able to come up with the solution to the equation in this class, but we can certainly show that the left-hand side equals the right-hand side, right? And so that's how you prove that those represent wave equations. Now, those are not the kind of waves we really talk about in this class. The waves we talk about are the kind that come from an oscillating source. We're mainly going to talk about waves that look like this. And these are useful because in a lot of we can use these to explain phenomenon in a lot of we can use it to explain a lot of phenomena we observe in everyday life. Okay, that's good for us because if we had to write the real equations down, that'd be much more complicated. And so we can use those equations to explain a lot of phenomena that we observe. When you take 215, you'll see these equations used over and over to represent optical waves. So what are these waves? What are some of their properties? Well, these waves come in all kind of different frequencies. From very low frequencies to very high frequencies. From very long wavelengths to very short wavelengths. So long wavelengths are radio waves. And if you look in that picture, if you move to the right, the wavelengths get smaller, the frequencies get larger. Notice what the smallest, there you go, you have radio waves, microwaves, infrared waves. I mean, they span a large number of wavelengths. Look at the one that spans the smallest number of wavelengths. It's visible light. So, for example, microwaves and infrared, you observe those in molecular transitions, for example. Ultraviolet, you see them in atomic transitions when an electron goes from one state to another. Soft X-rays and hard X-rays, they come from accelerated charged particles. Gamma rays, they come from accelerated charged particles or nuclear decay. There's no borderline, there's no set borderline between one type of radiation to another. There's no borderline between microwaves and infrared waves, and you notice there's a big overlap. A lot of times we define them based on their source. For example, gamma rays and hard X-rays, really the difference between them is gamma rays, we usually associate them with coming from a nuclear decay. Hard X-rays, we associate them with coming from accelerated charged particles. Now, one more thing I want to say is that these waves, the modern physics point of view, electromagnetic field is described in terms of photons. A whole bunch of photons make up the electromagnetic field. Each photon has an energy. And the total energy of the field is made up of all the energy of all the photons in that field. These photons travel at the speed of light. They're the quanta that they're the particle that represents light. It's massless.
What's the H?
Oh yeah, I'll get to that in a second. H is called Planck's constant. If you've had chemistry, you might have seen this. And Planck's constant is 6.626 times 10 to minus 34 joule seconds. It has units of angular momentum. So energy is Planck's constant times c over lambda. That's the energy of each photon. And you notice is the frequency increases, the photon has more energy. The more it oscillates, the more energy. The greater the oscillation frequency, the more energy it has. Okay.
That's because greater oscillation means lower wavelength, right?
Yes.
Or smaller?
That's right, yeah. And so this diagram shows you the different types of waves that we've observed so far. And of course, now we've also observed gravitational waves, right? 2016, we observed gravitational waves. Now, what are the sources of electromagnetic waves? There's really only two sources of electromagnetic waves. One, you have electric charges that are accelerating. They produce electromagnetic radiation. regardless of the spectrum, whether it's gamma rays or whatever. Okay, or infrared. They produce, accelerated charges produce radiation. The other source comes from transitions in atoms. Now, when you get charges to oscillate in a wire, for example, they can produce waves. You can make them produce waves at a particular frequency. Common ones are those for AM and FM. To produce AM and FM, you basically have electrons accelerated at a certain rate in a wire, producing the frequencies that you see on the screen. Now, the other source of electromagnetic radiation comes from electrons making transitions in atoms, or electrons in molecules making transitions in molecules, or protons or neutrons making transitions in the nucleus. Now, those, of course, are much higher energy. For example, when an atom makes a transition from one state to another, from a higher energy level to a lower energy level, it can give off visible light, it can give off UV, and it can give off IR. Let me briefly say something about visible light. This you should know. One thing you should learn, especially on Physics 215, the visible light is from 400 to 700 nanometers. Okay, and to find the frequency range, you take the speed of light over 400 nanometers and the speed of light over 700 nanometers. And it gives you the range. Now again, this is not black and white, this range, okay? This is an approximate number. But this is the range for visible light. This basically represents what we can see. Everybody is, the sensitivity of everybody's eyes is different, okay? The visible light. But this is the typical range for visible light. So, how do we produce electromagnetic waves from oscillations? Imagine you have a wire, two wires, such that this is, we'll start with this being positively charged and this negatively charged. And we make these charges oscillate and these charges oscillate. As these oscillate back and forth, the electromagnetic field changes. You have an electromagnetic field that propagates outward, and the magnetic field circles around it because you have charge moving this way. You have current going in this direction. So you have an electric field going outward and a magnetic field circulating around the wire. When you're really close to the source, let's say 1 or 2 wavelengths from the source, okay, actually not 1 or 2, 2 to 10 wavelengths from the source, the electric and magnetic fields are very complicated. And in fact, they generally fall off as 1 over r squared. As you are about 10 wavelengths away from the source, then the electric field is proportional to 1 over r. The magnetic field is proportional to 1 over r. as you get far away from the source. They call that the far field. And that's what we're interested in. Okay, we're interested in what happens far away from the source. So again, you have this is a dipole, so you have the electric field oscillating back and forth here, so you're producing electromagnetic waves all the way around this wire, but then there's a magnetic field that forms a circle around the wire because of the charge dependent, the time dependent charge in the wire. You can detect these waves with another antenna, which you put parallel to it, because that's going to induce an electric field into it, and you can actually measure that. Or you can take a loop of wire and orient it perpendicular to the magnetic field so that there's a changing flux through the loop of wire. That's going to induce a current in that loop of wire, telling you that there is an electromagnetic wave. It's called a loop antenna. Now, electromagnetic waves, they carry energy, they carry linear momentum, and they carry angular momentum. So even though they're waves, they have particle-like behavior because they can transfer energy, they can transfer linear momentum, and they can transfer angular momentum. If you were to calculate the power per unit area emitted by an oscillating dipole, it would have a form that you see as shown in the figure, with the dipole oscillating vertically and the energy being radiated out in that blue pattern. If you were to measure the radiation along the axis of the dipole, you wouldn't get anything. However, if you wanted to measure the radiation at an angle theta with respect to the axis of the dipole, your power per unit area is proportional to sine squared theta. Any dipole that oscillates has that kind of form in terms of the power per unit area that's coming from the source. Even in an atom. If you had chemistry, you've probably seen a picture like this in chemistry. Okay, so now I'm going to talk a little bit more about the mathematical part. I want to look at the energy flow just one second. Let me just check. I just want to check my time. I want to talk about the energy flow of the electromagnetic waves through a thin box. So imagine we have energy going through a thin box. I want to look at the power per unit area going through our thin box. Okay, I didn't draw it there. It's not very thin, but okay. I'm going to make the thickness of the box dx. This area we'll call A. And energy is coming out of the box towards us. Okay? And so the electric field, the magnetic field, look at my colors, are oscillating in those directions, but the energy is coming towards us. Now the power per unit area is what we want to look at. Okay? We'll just write it as P over A. Now, what is the power per unit area? It's the energy per unit time that's coming out of that box. So let me write it that way. So P over A is going to be 1 over A du over dt. We'll write U as the energy that's coming through the box. Okay? And the total energy that's coming through is due to the energy density of the electric field and the energy density of the magnetic field. Okay? So the energy density of the electric field and the energy of the density of the magnetic field. So let's write du is equal to U sub B plus U sub E through this volume. These little u's are energy density. The big U is the total energy in the volume. The volume I have is A times dx. So what's du dt? That. But what's dx dt for a wave?
So could you say that again?
What's dx dt for an electromagnetic wave? What does that mean? The time rate of change in position. What is that? Isn't it the speed of light?
Yeah.
Okay. So now let's put this together. Let me use a different color now. The A's cancel. U sub B plus U sub E is just the total energy density due to both fields. And so 1 over A du over dt, this is the total energy density, so that's going to be, well, it's going to be the energy per unit volume for the electric field plus the energy per unit volume for the magnetic field times C. But E is C times B. If I substitute this in here, I get, again, B squared over 2 mu naught, and I get that 1 over A du over dt is B squared over mu naught times C. We can also write it as, using, again, this relationship, check my math. B times E over mu naught. Now, since the wave is traveling towards us, and these two are perpendicular to the direction of travel of wave, I can define something that represents the flow of energy through this box. I can define something that represents the flow of energy through the surface of the box, and I call it the Poynting vector. Which is going to be given by the letter S, is 1 over mu naught times E cross B. The direction of this is in the direction of travel of the wave. And it represents the amount of energy per unit area going through that box.
Why is Poynting spelled that way? Is it named after someone?
Yeah, it's named after somebody named, I think his name was John Poynting.
Okay.
It's not P-O-I-N-T. It's P-O-Y.
Yeah, I wasn't. Yeah, that's what I was like. Oh, that's different. So.
Yeah. And so this tells you everything about the wave. It tells you something about the direction of travel of the wave. It has information about the electric field and the magnetic field. Now, the intensity is the average of the magnitude of this. Now, what's the intensity? It's the average power per unit area, which is the magnitude of S average. Well, this represents an instantaneous value. If I take the average of that, I'm going to end up taking the average of cosine squared because we're assuming sinusoidally varying waves. This will have a cosine term, that's the cosine term. I'm going to get a cosine squared. What's the average of cosine squared over a cycle? We did that last week. It's a half. And so the intensity, I, is E max, B max over 2 mu naught. Okay? Of course, we can rewrite this, right? We can rewrite it in terms of E only or B only because of the relationship between E and B. So we can write it as E max squared over 2C mu naught, or you can write it as C B squared over 2 mu naught. These are M's now, because these are from average values. So that's the intensity. It's the power per unit area emitted from the source. Okay? When I talked about the power per unit area, that I was talking about the intensity. It's an average value. And this can also be written as C times U average. Okay? Right here. Take the average of this times C, and that'll give you the intensity. You'll notice I'm just throwing a bunch of equations at you. Okay, now that we've sort of basically mentioned all the properties of the waves, let's do an example of everything here. This is a very important problem. Okay, so I know I have a lot of equations on the board. So on the equation sheet, you'll see a lot of different equations. That's what I was saying, is I throw a lot of equations at you in this chapter. So suppose we have a wave that has a frequency of 10 to the 8th hertz, E is 50 volts per meter. The wave is traveling in X direction. The minus X direction. I want to know the wavelength of the wave, the average energy density, the Poynting vector. I want to write down the equations for the electric and magnetic field. I'm also told that the electric field is perpendicular to the Z direction. So if this is F, omega is 2 pi F. 2 times pi is 6.28. Okay. What is the wavelength? Well, we know that C equals F lambda. So lambda is what? C over F. 3 times 10 to the 8th meters per second divided by 10 to the 8th hertz equals 3 meters. So the wavelength is 3 meters. K is 2 pi over lambda, which is going to be 6.28 over 3, is 2.09 per meter. Now, if E is this, what's B? If E max is this, what's B max? Well, that's E over C. If you do the math, you will get that the maximum intensity is 1.67. Can't read my handwriting, sorry. Times 10 to the minus 7 Tesla. So I can write the equation for the electric field. It's the magnitude times cosine of kx. And since it's traveling in a negative x direction, that's a plus. This has to be x because that's the direction of travel of the wave. Omega t. Oh, what's omega? Oh, it's 6.28. What direction is this in?
The negative x.
What direction
Right.
is the oscillation in? This is the direction of travel, but it says the direction of travel is in negative x direction.
So then it's in the, is it in the y because it's perpendicular to the z direction?
Yeah, so it's in the y. So it can be either. I wasn't very specific, right? It's either plus or minus y direction, isn't it?
Yeah.
Okay. And then b is capital T. Same term now for the magnetic field.
Shouldn't it be a 6.28 times 10 to the 8 times time?
Yes. Sorry.
Okay.
Thank you. This also has to be plus or minus, right? If this is plus, this is plus. If this is minus, that's minus.
Yeah.
Okay. No, I have it backwards. Sorry. If this is plus, that's minus. If that's minus, that's plus. It's got to agree with the right-hand rule.
What do we write it then as minus plus instead of plus or minus?
What I would do is just choose one, right? So, I know that this has to be in the minus I hat direction. So if this is the j hat, if I choose the positive j hat, then what direction must this be? It'll end up being the minus k hat direction.
Yeah.
So on an exam, if I wrote it like that, you would choose one or the other. You don't need to tell me both. Oh, what's the average energy density? What's the average energy density? It wants U total average. I can basically calculate 1/2 epsilon naught E squared max, and that'll give me U total average because the maximum value of the electric field and the maximum value of the magnetic field are going to be the same. Otherwise, I got to do this. This ends up being, I mean, you got to take the average. When you take the average of this, you get the 1/2 in front. And I'm running out of space, so I can't write all the units down. Let me see if I have that value written down. Yeah, I have 1.1 times 10 to the minus 8 joules per meter cubed. And then the last item is the pointing vector. The average pointing vector, which will give me the intensity. So let me check my, okay. So the average pointing vector then going to be that, which I had written before. And if you plug in the values in, and this is going to be in the I-hat direction. Be minus 3.33 watts per meter squared in the I-hat direction. Questions on that?
For the S average, is that 1 over mu naught on the top?
This is 1 over mu naught, but then the...
Okay, there's
well,
just
yeah,
a
but
glare
then
right there.
I put average here, right?
Yeah.
Should be like that, because it's E cross B.
Oh, okay. So
Let me
it's
rewrite.
-1.
Let me rewrite
There's
it.
just a
I'm
glare
sorry.
on the screen right there, so that's why it's...
Let me write it this way. That's better. Sorry, I did it too quick.
That's okay.
I apologize if you hear people talking outside. We have people working on a network out here.
No worries.
Are we okay with that? All right. Let's talk about how we represent waves. If you're close to the source, right? If you're close to the source, the waves from an oscillating source basically have a spherical shape. I mean, imagine dropping a pebble in a pond and looking at the waves that are formed by the falling rock. You just see the waves, the spheres get bigger and bigger as the wave travels outward. And as you get further and further away from the source, the radius of the waves get bigger and bigger, and they essentially become planar. And as a result, what happens is the amplitude essentially stays constant when you're really far away from the source. But when you're close to the source, the waves depend on, the amplitude of the waves depends on 1 over r. Okay? So the intensity of a wave from a source is P average over A. Okay, the intensity of a wave is P average over A. If I have a source of waves, and let's say we have spherical waves.
Cartographer.
Okay, as we get
Cartographer's cartograph.
Cartographer. Yeah.
as we get further away from the wave, the intensity decreases. So let's say over here, I is equal to P average over 4 pi r squared, where r is the radius of the sphere. If I had a device that measures the amount of energy I'm picking up here, the rate at which energy is being absorbed by that detector is going to be P average of the source over 4 pi r squared times the area of my detector. Okay. By the way, think about how the amplitude of the wave, the energy of the field is proportional to the square of the amplitude of the electric field or magnetic field. And we're saying that it's constant, but it really isn't. I mean, if you think about it, as this wave gets further and further away from the source, this sphere gets bigger and bigger. You have the same energy spread over the same sphere, right? The area of a sphere goes as r squared. All right, the energy of the sphere goes as r squared.
Yeah.
And the electric field goes as r squared. In order for the same energy to be on the sphere, the amplitude has to decrease by 1 over r. So that you have the same energy over the whole sphere. But when you're really far away from the source, the radius is so large that the energy is pretty much the same over each part of the wave. I mean, the amplitude doesn't change much as you get further and further away because you have plane waves. Okay. So your intensity, like I said, is P average over the area, the surface area of the sphere. The only kind of calculations we're going to do involving these involve the case where you have a spherical source, okay? Suppose we have some kind of source that emits spherical waves, and let's say P is 25 watts at wavelength lambda. What are the amplitudes, or what is the amplitude of the electric field 25 kilometers from the source?
So the 25 kilometers would be the radius, right?
I'm sorry? Yeah.
The 25, okay.
You're right, yeah. So then I is going to be 25 watts over 4 pi, because the surface area of the sphere is 4 pi r squared, right? 25 kilometers is 25,000 meters. And that's S average. Now, how do we write S average? There's a bunch of ways. Let me go back. So you have a whole bunch of equations we can choose from. Since we're looking for the electric field, we can write it as this way. And so E sub m squared is going to be 2 times C mu naught times this value. It's 2 times 3 times 10 to the 8th. And again, I apologize for not writing the numbers. I mean the units. And so I got to take the square root of both sides. And when I do so, I get, I have it written in your notes, 1.5 times 10 to the minus 3 newtons per coulomb for the magnitude of the electric field. Okay? By the way, I forgot a couple.
Is that?
I'm sorry?
Is that? Oh, that's after the square root, right?
Yeah, after the square root.
Okay, all right.
A couple more things to mention. You know, how we represent waves. These things that move outward are called the wave fronts. And sometimes we draw arrows to represent the waves. These are called rays. When we treat the wave as a particle, then we usually draw rays to represent the light. When we treat waves, when we treat light as a wave, then we draw either spherical wavefronts or plane wavefronts. These points, wavefronts, are points that are in the same phase. Like these would represent the peaks of the wave. There's different ways we represent the waves. And this distance here is the wavelength, even though my picture's bad, okay? They should be equally set. Those radii should increase by the same amount each time. Okay. Let me check the time. I want to do 2 more examples, and then I want to say a couple things. Because we got about 12 minutes left. Suppose we have a cube of side L. And its edges are parallel to the x, y, and z axis. So here are my axes. And I'm going to draw my axes this way. X, y, z. We have a uniform electric field in the x, parallel to the x-axis. And magnetic field, I'm sorry, the electric field is parallel to the y-axis. The magnetic field is in the x direction. What is the energy flow out of the cube? What is the total energy flow through this cube? The field is uniform. If the electric field is in the y direction and B is in the x direction, what is the direction of the pointing vector? What is the direction of the pointing vector? What's J cross I?
Is it negative K?
Negative K. So
Yeah, okay.
So let's assume that if the field is uniform, we can write E. So the wave is traveling this way. Right? This tells you the direction of the travel of the wave. The wave is traveling this way. True?
True.
So all I need to know is the flow of energy through this surface plus the flow of energy through this surface. So S is this way. Let me draw it in purple. And then it comes out the other direction. And then the normal to this surface points up. The normal to this surface points downward. So I want to look at the energy that passes through here. The energy per unit time, really, because S is the energy per unit area per unit time. Okay, so this represents the flow of energy per unit time per unit area. And the energy is going this way, so I got to take the dot product of S with the normal to the surface. And that's going to give me S top. Well, if I take the dot product of something in the minus K, these two in opposite directions, I'm going to get 1 over mu naught times E max, B max, and then I'll just put E and B. I have the cosine terms in here, cosine omega, cosine and cosine here, but I'm not going to write them down. And that's negative. S dotted with n bottom. These two vectors are parallel to each other. So I want to know the energy per unit time. So what can you say about S over this area? Well, since the electric field and magnetic field are uniform, S is constant through the whole area. So the power then through the top is minus 1 over mu naught E times B. The power through the bottom is plus 1 over mu naught E times B times the area. And when you add them, what do you get?
0.
0. Now, if I had a source inside, then it would not be 0. So what I've just done is calculated that the integral of S dot NdA
And that's only on a closed surface, right?
yes, the energy out of a closed surface. And if there were a source in there, then that means that the system is going to lose energy. And so that's going to be the time rate of change in which the energy is lost. And I was going to do this problem, but I think I don't have enough time to do this problem. And so basically the energy flow through here, well, the energy flow per unit time through here is this integral, and it's equal to the rate at which energy is lost in this volume. So either you have a source in here, or if this is not zero, you have some sort of source in here. I do want to say something interesting, though, about this example you're seeing on the screen. Even though I can't do the calculation because I don't have time. If you look at this problem, this is a capacitor that's charging. Look at the direction of the electric field. Look at the direction of the magnetic field. The magnetic field goes around the wire. The electric field points downward. The cross product of the electric field and the magnetic field is radially inward. That means as the capacitor charges, the energy is coming in from the sides. It's not coming through the wire. Do you guys see that? That when the capacitor is charging, the energy is coming radially inward. The flow of energy is radially inward. And that's what's okay. I mean, you just take E cross B in that particular example, and you'll see it's radially inward all the way around. Okay? So I'm going to just show you a couple more equations. I'll skip that. One can also show that the momentum of electromagnetic wave is given by the energy over C. The momentum absorbed by a particle depends on the total energy of the wave. One can show that. If a wave hits perpendicularly to a black body, the energy absorbed is U, and the momentum transferred is U over C. If the energy is reflected, then the total momentum that's transferred is 2U over C, but if it's at an angle, then it's 2U cosine theta over C. I want to mention these because of the fact that you might have a homework problem involving momentum transfer. One can also talk about the angular momentum transfer too, but we won't get into that. Any questions? I think we're at 2:05, right? Yeah. Any questions? Okay, so if you have no more questions, I have nothing else to say. So on Thursday, when you come to my office hours, I mean, I know there was a question regarding doing a review, but it's hard to do that because people might have various questions on homework, etc. But you can always ask me any questions you have on some concept you're having difficulty with. Okay?
Okay.
All right. So we'll see you on maybe on Thursday, for sure on Friday.
Thanks, Professor.
All right. Take care.